The second example in the specific heat section, right? We have a lead bullet here with a mass of 200 grams. It's traveling 120 meters per second, and then its initial temperature is 20 Celsius. And then we have a big block of ice here, 5 kilograms. Its initial temperature is 0 Celsius, and it's traveling to the left at 3 meters per second. The bullet comes and gets embedded into the ice. It gets embedded into the ice. Right? So this becomes a completely inelastic collision. So the kinetic energy of the system is lost, but the momentum of the system is conserved, right? So this is also a physics 1 application, right? So then it says assume 60% of the loss of the kinetic energy of the system, right, goes into heating the bullet, and 40% goes into melting the ice. So a little bit of the ice will melt, and then the temperature of the bullet is going to go up, right? So it says how much of the ice will melt and what is the T final of the bullet, right? Let's do a momentum collision problem, right? We have here the momentum of this, M1, V1, okay? And then the momentum of this is going to the left, minus M2, V2, and that's going to be equal to their combined mass, M1 plus M2 times V final. So let's calculate what their final velocity is as a combination, right? The mass of this is 0.2 kilogram, and then its velocity is 120, minus the mass of that is 5, its velocity is 3. The combined mass of the system is 5 plus 0.2 V final. So we have here the 24 minus 15 is equal to 5.2 V final. And then you're going to have 9 is equal to 5.2 V final. And they're going to the right at 1.731 meters per second. So that means the bullet's speed, which was really fast, it was 120 meters per second, goes all the way down to a speed of 1.731 meters per second, and it's going to the right. So it slowed down a lot. And what happened to the block of ice? It reversed directions. So it came to a stop, and then it reversed directions and is going to the right. So the bullet and the ice together are going this way. This is, of course, assuming that there's no friction on the surface, right? So then, what's the final kinetic energy of the system, and what's the initial kinetic energy of the system? Let's see how much kinetic energy is lost. So the final kinetic energy is very, very small. So there was almost like 100% loss of energy. Their momentums almost completely canceled each other, and you almost have 100% loss of energy. So now let's subtract those. The loss of kinetic energy is going to be 1462.5 minus 7.791, and then that one is going to be 1454.71 joules, right? Now 60% of that we're assuming is going to go into heating the bullet, right? So 60%, 0.6 of 1454.71, that's going to go into heating the bullet, right? So then we put the mass of the bullet, 0.2, times the specific heat of the bullet, times the change in temperature of the bullet, right? The specific heat of the bullet is 128 joules per kilogram Celsius. So then I'm going to convert this 200 grams into kilogram, right? 0.2 kilogram, and then the kilogram and the kilogram is going to cancel. And of course, this is joules again, and this is joules again, and therefore the joules cancels itself too. So the joules is gone, and then the change in temperature, right? So you have 0.2, 128 delta T, and then 0.6 times this, and then we can calculate delta T from this. Okay, since its initial temperature was 20, then we add 34.1 plus 20. That means the final temperature is going to be 54.1 Celsius, right? So its temperature goes up quite a bit, right? Then we can also calculate how much of the ice melts. So we have here 0.4 times 1454.71 times the mass of the ice that melts, right? For this ice, since it is at 0 degrees Celsius to begin with, we don't have to raise its temperature at all. We're going to melt it right away. So we have mass of the ice that melts times the heat of fusion of ice, and that's going to be 3.33 times 10 to the 5th. Okay? Kilogram, and of course we can convert that to grams, and therefore that will be mass of ice 1.747 grams. So again, not too much ice melts, only about close to 2 grams of ice melts, right? Then we can actually answer a subsequent question, right? What's going to happen in the interchange of heat between the bullet and the ice, right? Well, the bullet's temperature is going to go all the way down to 0, and then some more of the ice will melt, right? So how much more ice melts as a result of the fact that the bullet's temperature goes down to 0? So the interchange of heat between them. Okay, so 0.2, the specific heat of the bullet was 128. The change in temperature of the bullet, well, around 54.1 all the way down to 0, so this change in temperature is going to be 54.1. Right? Here we're taking the absolute value of this number. We're equating the absolute value of the heat lost by the bullet to the absolute value of the heat gained by the melted ice, right? So then that's going to be equal to the mass of the ice that melts times 3.33 times 10 to the 5th. Okay, and then we can calculate that. So 1.747 grams of ice melts initially, and then as a result of the interchange of heat between the bullet and the ice, 4.16 additional grams of ice melts as a result of the interchange of heat between them, right? And then the final temperature of the bullet is now at 0 degrees Celsius, right? After that, no interchange of heat happens. But then what's going to eventually happen, some more of the ice will melt due to the interchange of heat of the atmosphere with the ice, right? So eventually all of the ice will melt, and then finally the temperature of everything will reach the same temperature as the atmospheres, okay? Loss of kinetic energy of an inelastic collision going into heating the two objects, okay? Thank you very much.